Hello there, welcome to this video where I'm going to demonstrate how we can use trig functions to explain to students why we have these two equations that we use often in trig identities, in trig expressions when we simplify, and that actually that is based on the behavior and progression of the functions themselves. And I think that is an important link and connection to make in our discussion and the delivery of the lesson such as this, so that the learners can see that the function is not existing in isolation. It really helps to understand where the equations come from, and obviously later the identities that we end up even using, where they come from as well. Okay, so on the board, as you can see, I've sketched two functions, sine theta and cos theta, and I've indicated our frame of reference, the cast diagram, the order of the quadrants, as well as the angles. And it's also important to link the cast diagram to the functions themselves, and just for the students to know that the quadrants also can be seen here. So from 0 degrees to 90, we understand that to be quadrant 1, okay? And 90 to 180, that will be quadrant 2, that is quadrant 3, okay? Quadrant 4. And yes, of course, we have restricted our domain. Understand that these functions are oscillations all the way to infinity and from negative infinity. Okay, so we have created partition lines to help us visualize this diagram on the set of axes here. Okay, so this is our theta versus the y-axis type of setup here. So where are we? We are here in our point of discussion in this video. So let us take any angle or any acute angle and go sine 90 degrees minus 30 degrees. Why do we say this is equal to cos 30 degrees? And that is the big question of this video, right? So we know that 90 minus 30, that gives us 60. So where does the complementary nature of these two functions come from? When we look at the progression of the two functions in this interval here, or the restricted domain, well, the cosine is decreasing while the sine is increasing, okay? And when we locate the 60 degrees, 90 minus the 30 here, and this is a sketch, obviously not to scale, and so we go to the sine 60 degrees on the sine graph, we approximate. So there we are. And that is the point that is on the sine graph. Now to read off the corresponding y value, go to the y-axis, and before we even get there, we get to a point on the cosine graph now that also has the same y value. And according to what we've just done on that side of the board, that is 30 degrees, yes? And that will be whatever y value we get. So we can see that we observe what is called a many-to-one relation, okay? And I'm using the term loosely here because it's usually used in single functions such as the parabola, okay? So there are many theta values for one y value, okay? And similarly, we can talk about the cosine and say cos 90 degrees, okay? We can work with now minus, let's say, 45 degrees, okay? Where will that be? Right at this point of intersection. So that is 45. It's a point of intersection for both sine and cosine. So that will be equal to sine 45. Cos 45 is the same as sine 45, and that gives us a particular y value. Okay, so this is basically, studying the progression of the functions and looking at the type of relation that we have in terms of the correspondence of the y value, and that is what happens when we use these two functions, or why we can use these two equations in our simplifications of trig expressions as well as trig identities. Okay, so in the next part, I'm going to do the next set of equations when we're now moving to quadrant 2, 90 plus theta, and see how that is going to be used and applied in our mathematics. Right, so you'll see that I've sketched a green sine graph here, which is really a reflection of the blue one, the original sine graph here that is given, because I want to use it to explain the second equation here that we have as a reduction formula. Now look, sine 90 degrees plus theta is equal to cosine theta. Why do we say that? So let us use a numerical example. 90 degrees plus, let's say, 10 degrees. Okay, why do we say this is the same as cos 10 degrees? Because if you are here at 90 and you're adding 10 degrees, this will give you 100 degrees, right? So right here, just after the turning point, you want to read off the corresponding y value, and before you even get there, you meet a point on the cosine graph that also has the same y value, okay? And that will have a corresponding theta value of 10 degrees, whatever that y value is. So we can see that sine over 100 degrees is cos 10 degrees. So that explains the first reduction formula. The second reduction formula, let's use cos. So cos 90 degrees plus 60. Why do we say this is a negative sine 60 degrees? Because now if I'm at 90 on the cos graph and I add 60, I get to 150, suppose somewhere there. 50 degrees, we read off point here, okay, just the accuracy. We can see that there is another point on the negative sine theta graph that also has the same corresponding y value. So that will be our 60 degrees. Okay, so that is really the relationship that we see, which is called the complementary nature of the sine and cosine functions that we use in our reduction formulas in trigonometry so that we can simplify our stuff. I hope that was helpful to you, and I challenge you to now do the negative 90 degrees plus theta and then minus theta and play around with that and see how we can get the reduction formulas for that. So thank you for watching. See you next time.